Maths of the Coronavirus, Part 1, Exponential Growth. In this series, we're going to have a look at how the maths we learn in the class applies to understanding the coronavirus. Many of you might have seen this animation going around the net, which shows how the coronavirus spreads from person to person. Starts at one person, goes to three, and then more and more. It also shows how actions by specific people not to spread the virus can have a big impact further down the line. So let's have a bit of a look at the maths associated with that picture. Obviously this won't be as pretty as theirs was. So we start with one person who's sick, and then let's assume that they make two other people sick. Now, how many people they get to make sick depends on what's called the R number of the virus. Let's assume it's 2 though, because it makes our maths model a little easier. So here are our 2 new sick people. Now, if they don't do anything to prevent spreading the virus, they're going to make 2 other people sick, here and here. So now, in this next group, there are 4 people sick. And again, if they don't do anything to stop the spread, they're going to make 2 people sick each. And now we've got 8 new people sick at this point. Now, if we had all day and a piece of paper that was infinitely big, we could keep drawing this, but it would be nice if we could figure out some kind of pattern that would allow us to use maths. So let's have a look. In this first group, there's 1 person sick. In the next, there's 2 new sick people. Now 4. Now 8. Look at the numbers. 1, 2, 4, 8. They're doubling as you go up. We're timesing by 2. So our pattern is going to have something to do with timesing by 2. So let's have a look at timesing by 2. So we've got 2 times 2. Let's start with that. So 2 times 2 we know is 4. If we do it another time, 2 times 2 times 2, we get 8. Now if you know your indices, that's the same as 2 squared, and that's the same as 2 cubed. So let's go back to our little disease model here. That's the first stage of the illness, so the first spread there. That's the second stage, that's the third stage, and so on. And if we look at this number up here, the 2 or the 3, we can see that number lines up very nicely with that number. So in this stage, the third stage of the virus, there's 2 to the power of 3 people sick, or 8. In this second stage, it was 2 to the power of 2. 2 to the power of 2 is 4. Go back here, we've got 2 to the power of 1 if we follow the same pattern. And 2 to the power of 1 is indeed 2. And this is the 0 stage of the virus. This is where we started from. And so that's going to be 2 to the power of 0. And anything raised to the power of 0 is just 1. So now we've got a pattern. And it allows us to predict what will happen, and this is very important if you're trying to model disease, at the 6th stage. So when the virus spreads for the 6th time, it's going to be 2 to the power of 6. Now all you need is a calculator to figure that out. 2 to the power of 6. And that's going to be 64. Now that doesn't look too bad. That's only 64 sick people. But let's have a look what happens when I push it out to the 15th stage of the virus. So 15 spreads, nobody's done anything to stop it. And now the number of new sick people is 32,768. Again, not a super scary number, but let's double that number again. Let's go 30 stages of the virus, and 2 to the power of 30. And 2 to the power of 30 is a number just north of 1 billion people, right? So we're now greater than 1 billion people who have the virus at the 30th spread. So those numbers start to become pretty scary pretty quickly. The maths of the situation, we could say, is that D, which is the number of people that have the disease, is equal to 2 to the power of n, where n is how many times the virus is spread. And that particular type of equation, where we've got a letter or variable up in the top, is called an exponential equation, because we have an exponent, which is this up here, this letter up here as an index. So this is what we call an exponential equation. Let's take that exponential equation and put it here into a graphing calculator. So y is going to be 2 to the power of x. Now that's really very difficult to see. Let's sort of zoom that in a bit and see what's going on. So we start here at day 0 and we have 1 person sick. By day 1 we have 2 people sick. By day 2, 4 people, and so on. But let's have a look what happens as the days go on. I'm going to zoom out a little bit. And you can start to see that that grows really, really quickly. It doesn't take too many days, this is days along this axis, for the number of sick people to grow very, very fast. And that's the thing about exponential equations. They grow really, really quickly. Let's compare that to what's actually going on in the world. This is a graph of the number of people who have been diagnosed with coronavirus over time. And there you can see that same shape of curve. It's not exactly the same as our mathematical model, but the shape of the curve is the same as our exponential growth curve over in our graphing calculator. So what we're seeing is that the spread of the disease is very well modeled, that is to say we can create a mathematical version of it using an exponential equation. So what's the takeaway from today's little lesson? The takeaway is we have a type of equation called an exponential equation. And you know it's an exponential equation because you've got a variable up there in the index, what we call an exponent. Now the number down the bottom here can change, and we'll look at that in the next few lessons. But for the moment, this is an exponential equation. And an exponential equation, as you've seen from the graph, is a really good way of understanding how a virus, like the coronavirus, spreads. In the next lesson, we're going to look at a related concept to exponential equations called logarithms. So we're going to have a look at logs and how they relate to modeling the data, how they make it easy for us to understand how the virus is spreading, and how we can use them to make better graphs.